Hello everybody, this is the third video for Chapter 3 of the Statistical Learning course. So in the previous video, we've discussed feature selection or selection of explanatory variables. So when you have a regression model, so early on this chapter we introduced linear model. When you use a linear model to perform a regression, uh, it was seen that it can be desirable to try to screen out predictors that are irrelevant so as to reduce the variance of your prediction, and reducing the prediction variance should lead to better prediction as seen in chapter 1. Okay, so to reduce the variance of the predictions, one way is to remove irrelevant predictors. But then in this video, we're going to see another method to which uh, is meant to reduce prediction variances, which does not necessarily rely on simply eliminating irrelevant predictors. Okay, so we're going to introduce what we call shrinkage methods. So shrinkage, or sometimes they're also called regularization methods. These methods are another way to try to reduce the variance of predictions. There are many possible approaches to shrinkage, but we will study the two probably most famous ones, which are the ridge regression and the lasso regression. So the idea in shrinkage methods is that we're going to impose constraints on parameter values, or alternatively, we're going to try to shrink the parameters towards zero. Okay, so when we apply a linear regression, the parameters are free to move freely as they want, as long as they minimize the prediction errors in the training set. Okay, but now that we will impose some constraints on parameters, parameters won't be able to vary as freely as they were in the unconstrained case. So this will lead to smaller parameters. Smaller parameters will lead to smaller variance of predictions, because if you shrink the parameters, predictions will also be smaller. So in that case, your prediction will be less variable. On the downside, constraining parameters will incorporate bias to the predictions, okay? Because sometimes the predictions might be a bit smaller than they would be if there were no constraint on parameters. But the idea here is that if the decline in variance obtained is sufficient to at least offset the increase in bias, then we will have better predictions. Okay, so we saw earlier in chapter 1 that the mean square error of prediction for a completely new observation is a trade-off between variance and bias. So if you're able to reduce variance a lot without increasing bias much, then you can achieve better prediction performance. And this is the hope with shrinkage methods, is that we're going to try to shrink variance so as to have better predictions if we have limited increase in bias. Okay, so first we're going to introduce the ridge regression. So ridge regressions also consider linear models of the same form than a regular linear regression. Okay, so they use the assumption that the response variable is an intercept plus a linear combination of predictors plus a noise term. Okay, so this is exactly the same model than the regular linear regression. But what's going to change here is the way parameters are estimated here. So in the ridge regression, parameter estimates are chosen so as to minimize the following quantity. So we take the parameters, minimizing. This is the sum of square of predictions error. So this is exactly the same term than in an OLS regression. So it's the sum across all training observations of the response minus its associated prediction based on parameter estimate. And we have a square here, so this is squared. So this, if it will be only this, then this would be the regular OLS regression. But here a new term is added, plus lambda. So lambda is going to be a constant greater than 0 times the sum of betas squared. So time of the slope squared. And here notice that j starts at 1, not 0. So here the intercept parameter is not present in this summation. Okay, so what happens here is this new term imposes a penalty for large values of parameters. Okay, so because of that, parameters from a ridge regression, if they solve this problem and lambda is greater than 0, so not exactly 0, then the parameters will tend to be smaller than for the unconstrained regression, because large values of parameters are now penalized. Okay, so this solving a ridge regression instead of a regular OLS regression leads to parameters that are in average smaller, or in general smaller. So as we just said, the new additional term here, lambda times the sum of slopes squared, this penalizes large parameters, provided that lambda is greater than 0. If lambda is exactly equal to 0, then the regression is exactly the ordinary least squares regression. Okay. So this is why we can call it shrinkage, is using this. It's because using this approach has an effect on parameters, which is to shrink them. So by shrinking them, this has the effect of reducing the variance of parameter estimates. Okay, so recall that the true parameters beta, they are constant, but the estimators, they are random variables because they vary depending on the observations y you obtain, or even the predictors if they're random. So by shrinking them, we see that their variance will be smaller. Okay, you pressure them towards 0, so this has the effect of reducing their variance. Okay, so now a quick detail here. We noticed that in the previous ridge regression, no penalty is associated with the intercept here. Okay, so this is the traditional approach followed. It would be possible to penalize beta 0, but often it's deemed undesirable because the idea about the shrinkage method is we want to reduce the association between the variables and the basic the predictors within our regression. Okay, so and the idea here is that unless we have very strong evidence of covariation between the response and predictors, we'd like to dampen their effect. Okay, so as to have a bit more parsimony. Okay, so here, beta 0, it's not meant to reflect an association between the response and the predictors. Beta 0 is meant to reflect the average level of the target or the response. Okay, so because of that, beta 0 has a different interpretation than other variables, and often it's not deemed logical to shrink beta 0. Okay, so what we want to shrink often is the association between the response and the explanatory variables, not the overall level of the predictions. Okay, so we saw that the ridge regression objective function that is minimized offers a trade-off between accuracy and parsimony. Okay, so the first term, the sum of squared prediction error, tends to favor more accuracy because to reduce this term you need more accurate predictions. Whereas the second term favors some form of parsimony in the sense that it reduces the magnitude of parameters so as to provide less variance. So maybe it's not, maybe I shouldn't say parsimony, but instead I'll say smaller parameters. Okay, so ridge regression is a trade-off between accuracy and magnitude of parameters. So you want parameters that are sufficiently large so as to reduce prediction errors, but not too large so as to reduce the penalty term. Now, one thing we have to notice is that parameter lambda, we haven't said what the value of lambda should be. Okay, so what's the effect of lambda? Lambda determines the intensity of the shrinkage that is applied. So for instance, if lambda is 0 or very small, well, if lambda is 0, you have exactly an OLS regression, and if lambda is very, very small, you have almost an OLS regression because the second term will be negligible. So we can see that for low values of lambda, you have very little amount of shrinkage. Conversely, if you have large values of lambda, then the penalty term will be much more important than the accuracy term. So this will tend to favor very small parameters at all costs, even if predictions aren't very accurate. Okay, so and in between, of course, it's a spectrum. Okay, so when you increase lambda, you increase the amount of shrinkage being applied, so the intensity of the pressure you put on parameters to move towards 0. So lambda, it's often referred to as some tuning parameter because we will need a way to tune that parameter so as to make find the optimal trade-off between accuracy of predictions and variance of predictions. Okay, so now what we're going to do is we're going to solve the ridge regression. So for the ordinary OLS regression, we already had the a closed form for the solution of estimates of beta. But now we're going to generalize this the formula we had to ridge regressions. So to do that, we'll first need to introduce a bit of I'd say not terminology, but rather notation. So we have to introduce centered quantities. Okay, so what do we mean by that? We mean quantities where their sample mean is subtracted. Okay, so x star ij is the xij, so the jth predictor for observation I, minus x bar j, where this is the average value for the jth predictor in our data set. So x bar j is simply the average of xij in the data set. Same thing here, x star I is simply the response for observation I, where the sample average of the response is subtracted. And here, beta star will be the column vector of predictors, but here we've withdrawn beta 0. Okay, so here beta star is all predictors, all slopes of the model, and this does not include beta 0 because beta 0 is the intercept, not a slope. Here, y star is the column vector of all centered observations in the model, and x star is the design matrix for the centered model, which contains all centered observations here. Okay, so recall that when we say centered predictors, each column here has its own value for the average to center the observations. Okay, so here this is the first predictor. So all these are centered by subtracting x bar 1. All these are centered by subtracting x bar 2, etc., until all these are centered by considering x bar p. And x star here, it's the design matrix, so it's centered observation. And one small difference here with respect to the original design matrix is that our column of 1, which was there, is not there anymore. Because when you center the ones, the average of ones is just 1, so it would be a column of 0, and here we don't put it there. Okay. So this is the design matrix of centered observation, where the first column containing only 1 is not there anymore. Okay. So now we want to solve for the parameters beta within this ridge regression. So we will do that in 2 different steps. So the first step will be to find beta 0, and the second step will be to find the all other betas. And the reason why we have to do that is that beta 0, it's not found in the penalty here, so it must be treated a bit differently than other parameters. Okay, so we start by finding beta 0. So when we want to minimize this objective function, what we need to do is find first order conditions. So we differentiate with respect to beta 0 and let the derivative be equal to 0. So if we do that, then maybe I'll write a bit. So when we differentiate with respect to beta 0, because beta 0 is not there, this guy disappears. Then the 2 goes in front, and then the beta 0. Okay, so here the derivative of the interior with respect to beta 0 is a minus, so you can put a minus sign here, and we obtain that this quantity here must be equal to 0. Okay, so what you can do here, I'll call it quantity star means this quantity here. So if star must be equal to 0, what you can do, you can multiply on both sides by 1 over n and sum on both sides. Oh no, this summation is already there. Sorry about that. So you can have this instead. And if you do that, I invite you to do it at home, so you can pause the video and do it at home. But if you do that and you isolate beta 0, then you obtain the following relationship, which is beta 0 is y bar minus the sum of beta j's times x bar j. Okay, so this is exactly the same equation than in the regular OLS regression, and this is true because beta 0 is not found in that penalty term, so all the steps are the same. Okay, so this does not give you beta 0 by itself, but rather tells you how beta 0 is related in the other betas. Okay, but still we can use this equation to express the quantity above in terms of only beta 1 until beta p and remove the beta 0. Okay. So here, okay, let's go back one slide. We can take this equation and replace beta 0 here by, okay, so take this expression, which is the objective function, and replace beta 0 here by this quantity, plug it here. And if you do that, then the objective function, again, please try that at home. I won't do it here because I have no blackboard and it's a bit cumbersome, but please push and stop and make the following step. And if you do that, this should give you the following quantity. The objective function should be equal to this, where we want the problem becomes to minimize across all the betas from beta 1 to beta p of the following quantity. So here it's exactly the same thing, but instead what we have is centered observations. Okay, so there's no beta 0 anymore, and the original observations are replaced by their centered version if you substitute beta 0 and the original objective function. Okay, and then to go from here to here, the second line is just rewriting the first line in vectorial notation. Okay, so here we can replace this guy by the Cartesian product sorry, not Cartesian product, the dot product between the vector of y's minus, this is the vector, the design matrix times vector beta. So here, instead of having the dot product, what we can do is take the vector transpose times the column vector. So when you do that, you obtain the dot product, because you sum all products of elements between this vector and itself transposed. So here this can be written as y star minus x star beta star transpose times this. If you're not convinced, once again, press on stop. Try doing it yourself until you get that expression. And here, same thing for this new term. This is lambda times the vector beta star transpose times the vector beta. Okay, so then that's good. And finally, to go from the second line to the third line, the only thing we do is to expand that squared here. Okay, so that squared is y star times transpose times y star minus this guy transpose times y star plus y star transpose times minus this guy plus minus this guy transpose times minus this guy. Okay, so to go from here to here, this is simply expanding the square. And here, so to minimize this expression with respect to beta star, we once again have to find first order conditions. And then what we will do here to speed up computations is we'll find the first order conditions in a vectorial manner. Okay, so we'll differentiate with respect to beta star, which means we'll differentiate with respect to each element of the vector beta star. And here this derivative should be equal to 0, but not a scalar 0, but instead a vector of 0, which means that derivatives with respect to all elements of beta star should be equal to 0. Okay, so if we do that, we can apply the vector differentiation rules that we've learned in our in the preliminary slides. So here there's no beta, so this term disappears. Here this is beta star times this, so this, what happens is the vector beta simply vanishes if we follow the rules seen earlier, but because we had different derivative with respect to x of x transpose u must be equal to the vector u. And same thing here for okay, so this is true. Yes, this is true. Okay, and the reason why there's a 2 here, maybe let's go back one slide, it's because if we go here, then one term was x star beta transpose times y star, and another term was y star transpose times x beta star. Okay, but these two terms, sorry, this is transpose, but these two terms, they're exactly the same, because this guy here is 1 by 1. So it's a row vector times a column vector, so it's 1 by 1. So if you transpose this guy, you still get the same thing. And recall that AB transpose is equal to B transposed A transposed. Okay? In general, for any matrix AB, that where the product is well defined. So this quantity, if you transpose it, it becomes y transpose times this whole thing transpose transpose, and transpose transpose means just untransposed. Okay, so this is why the 2 appears here. It's because it regroups two terms that are exactly equal. Okay, so let's go back to the next slide where we were differentiating. Okay, so here we said this term vanishes, the beta here vanishes. And then we had something of the form d here with respect to x was simply twice, or when a was symmetrical, this was here. Okay, maybe I shouldn't use x because we already use x below. I'll use u instead. So derivative with respect to u of, so here u is a vector, a is a matrix. So if a is symmetrical, then this twice, this is the answer, twice a u. And here, if you look here, this guy inside x transpose x, it must be symmetrical, because if you transpose it, it becomes x transpose times x transpose transpose, which is x times transpose times x. So this guy is symmetrical, so we can apply the above rule, which becomes 2 times x transpose x times beta with stars everywhere. And same thing here for that last term. We have lambda times, then this beta disappears here and is replaced by a 2. So this becomes I beta star. And of course, the identity here, it can vanish, but we keep it there to make it more convenient at the next slide. Okay, so here, differentiating this and equating this to 0 leads to the following equation here. And then what we're trying to find here is beta. So what we can do here is simply isolate beta here. And so if we do that, we have something like, let's write it. We have, okay, whoops. 2 times x transpose. I won't put the star, but let's say the star is there for all the symbols. Okay, just to make that notation more easy, I won't put the star, but plus lambda I beta is equal to 2 times x transpose y. Okay, so of course we can simplify the 2 here. And then if we want to find the beta star, what we need to do is simply to multiply by the inverse of this guy on both sides. And this becomes exactly this expression here. So this is the solution for a ridge regression. And we see that if lambda is 0, this term vanishes and we get back the same original solution than for the original OLS regression, which is nice. Okay, now one legitimate question is the following. So, whoops. Does the inverse of this matrix exist? And the answer is yes. So why is that the case? It's because x star t x star is always positive semi-definite. Okay, why is that the case? I'll let you try it, but if you have u transpose, okay, so u transpose again. Here I will drop the stars, but let's say this star is there. So for any u here, if you have that, this is equal to xu transposed times xu, which is the dot product between the vector xu and itself. So this guy must always be greater or equal to 0, which means that x star transpose x star is positive semi-definite. Okay, so here, moreover, because we add this additional term, the resulting matrix is not, well, it is still positive semi-definite, but even stronger than that, for lambda greater than 0, it must be positive definite. So why is that the case? It's because when we have u transpose identity u, this is equal to u transpose u, which is strictly greater than 0 provided that the vector u is different than 0. So for that reason, this matrix here must be positive definite, and for that reason it can be shown if you apply linear algebra results, then the inverse of this matrix must exist. So this guy really makes sense. Okay, you can always consider this quantity. Okay, so that's great. We've solved the ridge regression. We found the parameter estimates, which stem from that optimization problem, which is a ridge regression. The solution is known in closed form in terms of the predictor variables and the response here. This is the solution. Okay, so what are the limiting cases? Well, again, for different values of lambda, you will get different results. Okay, if we go back here, the solution depends on lambda. So if lambda is equal to 1, you're going to get one set of parameters. If lambda is equal to 3, you're going to get another set of parameters, etc. So lambda, when you vary its value, you will vary the solution. But now what are the limiting cases? As we said, if lambda is equal to 0, we get back the OLS, which makes sense because we impose 0 penalty on parameters, so we get back to the original unconstrained case. And conversely, if lambda tends to infinity, then this part will become negligible with respect to this term as lambda becomes extremely large, and therefore this the inverse of this will simply be approximately 1 over lambda, which times the identity matrix which will be close to 0, which will converge to 0. Okay, so as lambda increases to infinity, this converges to a matrix of zeros, and therefore beta star converges to 0 also. Okay, so we see that as you increase lambda to infinity, the parameters are infinitely shrink so as to eventually converge all to 0. So in practice, how do we choose lambda? Again, the purpose is to find the suitable trade-off between bias and variance of predictions. So one way to do this, which is I'd say the most typical way, is through out of sample performance assessment. So for example, cross validation. Okay, so you train your model on the training set for various values of lambda. For all such values of lambda, you can make every value of lambda individually, you can make predictions for your out of sample set, check predictions, prediction errors, then average them, or average their square prediction errors, and have your out of sample MSE or validation MSE, and you have one out of sample MSE for each value of lambda. So then when comes the time to select lambda, you will pick the lambda which leads to the smallest out of sample MSE so as to produce the best accuracy out of sample for prediction. Okay, so if you do that, then the optimal lambda most likely will not be 0, will not be infinity, would be somewhere between, and that somewhere represents the optimal trade-off between squared bias and prediction variance so as to lead to the best prediction for new unseen observations in the validation set. Okay, now one quick detail about ridge regressions that we should mention is scale invariance. So if you apply regular OLS regression, you can change the scale of your predictor. For example, multiply them by some constant, and this would not impact your predictions at all. Okay, so why is that the case? It's because if you apply a linear regression, if you take a predictor xj and replace it in the data by xj times c, where c is some constant different than 0, then the only thing that's going to happen when you run the new regression is your old estimate beta j will be replaced by beta j hat divided by C, so that when you do the product between your new predictor and your new slope, then both will cancel out, and ultimately you'll get the same product, so your predictions will not change. Okay, so predictions in OLS regression, they're invariant to the scale of your predictors. Now, does the same happen for ridge regressions? So if you try to do that, if you take a parameter and scale it by multiplying by some constant c, which is, for example, greater than 0, so what would happen if you in the optimization, if you took the original slope, optimal slope, and divided it by c? Of course, the product would remain the same, so the prediction errors would remain exactly the same. However, the penalty term, which depends on the summation of squared betas, would change in that case when you replace the original slope by the new slope. So because of that, your slope that was initially optimal in the original regression, once you've scaled your predictor in the second regression, because you changed the penalty associated with the beta, when you scale that new slope, the old set of parameters might not be optimal anymore for the new regression. Okay, so ridge regressions are impacted by the scale of your predictors, unlike OLS regression. So for this reason, what's often suggested, okay, it's not, I don't say this is something you have to do, but people sometimes do that, which makes a lot of sense, is that they scale the predictors before applying the ridge regression. So what do we mean by scaling? We mean that before applying a ridge regression, instead of taking original predictors, people use scaled predictors, which is the following. They take, for example, xij is the ith observation for predictor j. So they subtract its sample mean and they divide by the sample standard deviation for that variable. So here you get new predictors x till ij, where their sample mean for each j would be exactly 0, and sample standard deviation for each j, when you take the deviation across I, it would be exactly 1. Okay, so for this reason, when you scale predictors, you ensure that all predictors are on the same scale, and when you apply the penalty, so recall the penalty is lambda times the sum of beta j squares. So having predictors on the same scale does not penalize one predictor and ensures that the betas should also be roughly on the same scale. So when you apply this penalty, you penalize somewhat fairly all the predictors instead of only penalizing predictors which have a very small magnitude. Okay, so if there were predictors which would have small magnitudes, corresponding slopes should be very large to compensate, and they would be heavily penalized. So this is not something we want. So for that reason, it's often recommended to scale your predictors when you apply a regression, a ridge regression. And of course, this is not needed if you apply ordinary least squares, because the predictions are scale invariant. Okay, so this was a first representation of the ridge regression. So a first way to perceive ridge regression. Now, what we're going to do is discuss a second problem that leads to the same answer. Okay, so we can rederive the ridge regression from an alternative optimization problem. Okay, so what if we consider the following problem instead? So let's say we could try to find the parameters beta 0 until beta p, which would once again minimize the sum of squared predictions error. So this is the same thing before, but instead of applying the following penalty, so this was the ridge regression penalty that we shown earlier. Instead, what we're going to do is we're going to impose a constraint, which is the following form. We will impose that the sum of beta squared should be smaller or equal to some given s. So instead of adding a penalty term in the objective function, we're going to use the original objective function of the OLS regression, but instead we're going to impose a constraint where the sum of squared parameters beta, which this starts at 1, so the intercept is once again excluded. This must be smaller or equal to s for some constant s greater than 0. So then if we have this problem, this problem here, it can be shown, which we will do next, that for this problem, the solution is exactly equal to the same solution than for the ridge regression for some lambda. Okay, so for each value of s here, there will exist a lambda such that the solution to this is beta ridge regression with parameters lambda, and vice versa. So for every lambda of the original ridge regression that we had, there will exist an s such that the solution is also a solution to this. Okay, so we see that both problems, the original problem with this ridge regression penalty and this new problem which instead imposes a constraint on the sum of parameters, they have exactly the same solution up to like one. You have to find an equivalence between the lambda of the first problem and the s of the second problem. But once you have that mapping where you find the right lambda corresponding to the right s, then the answers from both problems are the same. So let's show that now. So we're going to provide a sketch of the proof here. So let's go back here. This is a constraint optimization problem. Okay, so if you've done I hope all of you have done a calculus class. If you've done that class, then you should know that to solve continuous constraint optimization problems, a common technique is to use Lagrange multipliers. So to do that, what we'll do is to define the Lagrangian, which is to take the objective function and add lambda times this guy minus s. Okay, because what you do to define the Lagrangian, you take the original objective function plus lambda. So lambda stands as the Lagrange multiplier times the constraint here that must be either greater or equal, or here it's smaller or equal to 0. And once you have that Lagrangian, to find the answer to the optimization problem, you have to differentiate with respect to all of the betas. Okay, so if you do that, so for example, for any j in 1 to p, any explanatory variable, if you take the first order condition of this and you differentiate this Lagrangian with respect to beta j, what you obtain here, so this 2 goes in front, the minus sign goes in front also. So, and here what happens is the differentiation derivative of this guy with respect to beta j is just twice lambda beta j. So we see here that this first order condition, is exactly the same that you had for the ridge regression. So if you go back in your slides, again, feel free to click pause here and go back to the previous slide. But you can see that this entails a system of equation for all values of j in 1 to p. And this system equation is exactly the same system of equations you had for the ridge regression. So if the solution for both problems solve the same system of equation, well, again, the solution must be exactly the same. Okay, so this completes the sketch of proof. Both the original problem, which has a penalty term for the betas, and the second problem, which has instead a constraint on the sum of squared betas, they lead to the same system of equations and their solution, so they lead exactly to the same solution. Okay, so this gives two different ways to see ridge regression. It's either a regression where you penalize the betas or a regression when you constrain the betas. Okay, so we've mentioned two ways to shrink the variance of predictions. The first approach, which we saw in the last video, was to try to remove unnecessary or irrelevant predictors. Okay, so you can call that approach best predictor subset, where you're trying to find a subset of predictors which are relevant, and by eliminating the other predictors, you should shrink variance of your predictions. Conversely, the ridge regression doesn't attempt to filter out irrelevant predictors, but it shrinks the betas so as to shrink the impact of noise, and this, yes, incorporates bias, but at the same time it reduces the variance, and sometimes the reduction in variance is better than the increase of bias. So why is that the case? For example, if you do let's just give an example. So if you do an ordinary linear regression on a data set, and in the data set you have predictors that are irrelevant. Well, these predictors, they will have slopes that are not exactly zero. Okay, they might be close to zero, but they won't be exactly zero, and for that reason they'll generate noise. So when you apply shrinkage, the slopes of these irrelevant predictors should be shrunk, and shrinking their slope will reduce the variance instead, because you have less noise generated by these irrelevant predictors. Okay, so now what are the advantages of a ridge regression with respect to the best predictor subset? Well, a clear advantage is the speed of computation. Okay, so we discussed last time that if you want to find the best subset of predictors across all possible sets of predictors, then you had 2 to the power p models to consider, and if you want to train them all, it might be too long. Even if you use a stepwise approach, instead of having 2 to the power p, you might have something of order p squared, but this is still a lot of models to train. Conversely, when you apply a ridge regression, what you need to do is you have one ridge regression per possible value of lambda, because you want to at least compare all values of lambda out of sample. But if you have, let's say, 100 values of lambda to consider, then you have to have 100 model result. Okay, so you might think, well, this is still very long, but there's a result which entails that if you find the solution for one value of lambda, then you can solve simultaneously for almost simultaneously. So through minimal additional computations, you can find the solution for all values of lambda at the same time. So if you want to test for 100 values of lambda, it's almost as quick as if you test for a single value of lambda. So the running time for ridge regression is not much faster. It's not much slower than for a single run of lambda. And even better, so the ridge regression is known in closed form, so it's not very nasty to compute. Okay, so okay, one detail here, I said it's known in closed form, but typically many packages, they don't invert the matrix and the expression of the solution. Instead, they solve a system of equation which is a bit quicker and maybe more stable numerically. But I won't get into these numerical details. Let's say this is out of scope of the current material. Okay, but the idea here is often ridge regressions are much quicker to compute than best predictor selection in terms of if you want to reduce the variance of your predictions within a regression. Okay, but now, is there a disadvantage of using a ridge regression with respect to the best predictor selection? And the answer is yes. Because when you apply a ridge regression, your result will still retain all parameters except their coefficients will be shrunk towards zero. Okay, and no predictor will have a beta which starts from a non-zero value, which is shrunk, to a zero value when lambda is increased. Okay, so applying a the ridge regression instead of an OLS regression will simply shrink the betas, but it will not set them to zero. So you will retain all predictors of your model, which leads to a model that is not very parsimonious. Okay, so if you have originally 100 predictors in your data set, if you apply a ridge regression, you'll still get 100 predictors at the end. This is different than for best subset of predictors, because for the latter approach, if you had 100 predictors originally, maybe by applying the stepwise algorithm or something like that, you might end up with 6 predictors at the end. So we can see that from the standpoint of model interpretation, applying a best subset of predictors approach might be preferable to some ridge regression. Okay, so now in terms of comparison between the ridge regression and the best subset of predictors, is there a way to express both optimization problems in similar way? And the answer is yes. Okay, so it can be seen that solving the problem of the best subset of predictors is equivalent to solving the following problem. So if we want to find, for example, the best subset of exactly capital N predictors, which leads to the best possible regression, then it's equivalent to solving the following. It's equivalent to solving to find the set of betas which minimize the sum of squared prediction errors, again, subject to the following constraint, where the sum of indicators, which are 1 if the beta j is different than 0, and 0 if beta j is 0, must be smaller or equal to n. Okay, so here, every time a predictor is different than 0, this indicator is 1. So this guy here represents the number of non-null parameters, or non-null betas, okay, excluding beta 0, but non-null slopes, let's say. So here we see that the best finding the best subset of capital N parameters or predictors is equivalent to solving a problem which looks like a bit the ridge regression, but instead of having a constraint that instead of having this constraint for the ridge regression, finding the best subset has another kind of constraint, which is of this form instead. So we see that both problems are analogous, but what changes between the ridge regression and the best predictor subset is the constraint or the budget allowed for parameters to depart from 0 or small values. Okay, so both try to reduce the same objective function but under different constraints. One is to have a number of parameters different than 0 that is limited, and the other one is to have the overall magnitude of squared parameters, which is limited. Okay, so as we said, what differentiates the ridge regression and the best predictor subset selection is simply the form of well, we can call it the penalty term, but it's really the constraint term. And the constraint term is to, as we said, to limit the magnitude of parameters in the ridge regression, or to limit the number of predictors different than 0 for best subset selection. Okay, so two approaches can be seen as similar problems, but which assign a different budget for how large the coefficients beta 1 until beta p can be. So we will stop there, and next time we will see an approach which combines positive features of both approaches. So have a nice day. I'll see you next time.